Okay, so we're looking here at section 2.3 and just this idea of a hypothesis test. And this is a very technical thing. I mean, you know, you can kind of have an intuitive idea of it, but it's also a very technical thing. So in a hypothesis test, we always have a null hypothesis, H0, and it is always a very specific assumption. You know, think equality. If you're trying to think of a null hypothesis that says something like less than or greater than or something like that, it's wrong. Okay, we have, you know, A is equal to B, you know, or A is equal to B is equal to C is equal to D, you know, oops. You know, things like that. The null hypothesis is always about a specific situation. And then the alternate okay, so the alternate hypothesis is some or all of everything else. Okay, so for instance, if H0 is that I have some proportion is equal to 0.4, then HA would typically be one of three things. It could be that P is not equal to 0.4. Okay, that's all of everything else. Okay, or it might be P is, say, greater than 0.4, that's part, or P is less than 0.4, that's part. Now, for the most part, we are mostly looking at this, although our project in this module is actually looking at a greater than situation. Okay, so this is our project looks at what we call a one-sided alternative, mostly because for simulation purposes and so forth, and to get started, it's just way easier to think about, and so we do our project this way. But actually most of our work is going to be with what we call a two-sided in this not equal, where it's all of everything else. Now, you know, but this is where, you know, if I had something like H0 and I had averages from three different things, so x1 bar is equal to x2 bar is equal to x3 bar. I think all these averages are the same. Well, then HA for us would be, in this case, everything else would say at least one average is not the same. Now, it could be all three are not the same, but the full of everything else is that at least one is not the same. Okay, so that's what we have for null and alternative hypothesis. Again, you know, you are just flat out wrong about your null hypothesis, if you do not have stuff that are all about an equality of one specific case. Okay, and basically that boils down to, because if you try to do anything else, it's too hard, we don't know how. Okay, so part of the reason we go with this structure is we know how to do it, and therefore that's what we're going to do. If if we didn't know how to do it, well, then there'd be no point in having a class, I guess. Oh, the wonderful things in life, right? So we have this case every single time that null hypothesis is some equality, and this is what we assume when we do our work. Okay, we assume our null hypothesis when we go to do our work in determining a distribution. Now, what we get from this is, they're kind of these basic parts of a test. Okay, one is our pair of H0 HA. We need that. We need our data. Okay, we go collect data from a sample. Not sure why that jumped up, but hey. We go collect data from a sample, and we need a particular test. So we need a type of test, because there are all kinds of them out there. So we need to match our type of test with our our hypotheses and our data. We have to make this match. Okay, and so that's why we have all this time in the class, is a lot of different types of hypotheses and data, and therefore we can have a lot of different types of tests. But they all come together to do the same sort of thing. So we do this, and then sort of the output of all this, the final portion, is our p-value. Okay, and this is always the same thing. It always means the same thing, and our p-value is the probability or likelihood okay, so it's a probability or likelihood of having our data or more extreme, more extreme data that go against the null hypothesis. Okay, it goes against the assumption. Now your textbook, puts it in a little bit different frame. So your text, and this is fine too. I think whatever kind of works intuitively for you. So your text says your p-value is that probability of observing data at least as favorable as yours for the null hypothesis. Oh, sorry, the null hypothesis. I misspoke there. The alternative hypothesis. Okay, they're both saying the same thing. So, you know, here they're looking at it in terms of the alternate hypothesis. Is you have some data that are out there, and they maybe don't really seem to fit the null hypothesis. They seem to favor the alternate hypothesis more. And so you could talk about the p-value as the probability of finding more data like that that support that null hypothesis, sorry, I keep saying that null, that support that alternative hypothesis. Or you can think of it as, hey, you had this null hypothesis, your data don't fit it. I mean, because if your data fit the null hypothesis, there's no reason to go through all this statistical tests, right? You know, if I'm wondering if a person is flipping a fair coin and I flip it and I get 5 heads, 5 tails, I'm going to quit wondering, right? There's nothing more to do there. So, you know, if my data fit the null hypothesis, I'm done. I don't care. But if I got 6 heads, 4 tails, oh, well, maybe it's fair. I'm not sure. Well, it'd be nice to have a number. That's the p-value. You know, what's the probability of having our data or something more extreme? You know, so I got 6 heads, 4 tails. Well, more extreme would be like 7 heads, 3 tails, and so forth. But if my null hypothesis is a fair coin, 50-50, you see, I'm going more extreme, and it's going against the null hypothesis. But if it's going against the null hypothesis, another way to view it is it's going for the alternate hypothesis. So either view of what that p-value is, it's the same thing, you know. So you can either think of it as evidence for your alternative or evidence against the null. Now, since we tend to reject the null, that's the language, you know, I tend to go with against the null, but we say we reject the null in favor of the alternative. Oh, well, so it's favorable. So whichever floats your boat, it's best if you get that they're both saying the same thing. But that is what a p-value tells us. And so you see, you know, a p-value equal 0.001, you know, says that under that null, right? So it says given whatever our H0 is, I have only a 1 in 1,000 chance of observing this extreme. Okay, so I only have a 1 in 1,000 chance of observing this extreme. And so, oh, well, then I don't think the null hypothesis is very likely, right? And so a really small p-value is very damning to a null hypothesis. A large p-value is much more supportive to a null hypothesis, because it says, oh yeah, if the null hypothesis is true, you know, say I've got a p-value of 0.3, oh, then I might see these data 30% of the time. Well, that's pretty often. And so, oh yeah, okay. That seems to, help with the null hypothesis. It doesn't, never do we prove the null hypothesis. And again, it's just kind of the nature of the beast. But so there, we'll stop there with our initial dive into hypothesis testing and this p-value idea.